Okay, right. So I want to tell you about a paper that appeared last month and that I wrote in collaboration with Jonathan Heckman and Shritra Mudir here at UPenn. And so the title of the talk and the paper is the same, on the holographic dual of a topological symmetry operator. And so this talk is going to be it's going to lie at the intersection of holography and generalized global symmetries. And I want to motivate the key questions that I aim to address by recalling slogans, features of these two subfields. So first, if we're given a conformal field theory with a semi-classical gravitational dual, then we, generally speaking, have the expectation that any operator of the boundary CFT should have some bulk counterpart. This is one aspect of the holographic dictionary. The generalized symmetries slogan that I want to recall is the slogan of the whole program, namely that symmetries of a quantum field theory should be thought of as generated by topological operators, and conversely, any topological operator generates a symmetry of a QFT. And so putting these two things together in context of holography, we get the following set of questions. If we're given a conformal field theory with a gravitational dual and a global symmetry operator and a global symmetry, we can ask what are the bulk counterparts of the associated topological symmetry operators? Do they exist? What are their properties? And we know the answer to these questions very well in the context of string holography. This goes back to work in Oxford, Durham, Johns Hopkins, and there's been more since. In these cases, in a large class of examples, a topological operator at the boundary CFT pulls off to become some dynamical brane in the bulk. In particular, it's a non-topological object. And so the general expectation might be that this is a generic feature, that whenever we pull off a topological operator, we get some extended non-dynamical object in the bulk. And the goal of this talk is going to be to argue for this via some bottom-up considerations. So in particular, there'll be no top-down discussion, no string theory allowed. And one consequence of arguing that topological operators become non-topological in the bulk is going to be a no global symmetry statement. And it is via this no global symmetry statement that we connect to previous literature that I'm going to start reviewing next. But before I do that, let me quickly check if there are any questions regarding motivation or where we're heading. Okay. So the piece of work that I would like to review was completed in 2018 and was titled Symmetries of Quantum Field Theories and Quantum Gravity, and authored by Harlow and Oguri. So the reason I've decided I'm going to review this is because when we were circulating our draft, we were often asked to put our results into context with theirs. Another good reason is that, to my understanding, this is the first piece of work that introduces subregion duality into the study of symmetries. This is a very deep concept, and a great application is made in their paper. And then finally, they prove this no global symmetries theorem here that I've written out. So the statement there is that no quantum gravity theory in asymptotically ADS space, which has a global symmetry, can be dual to a boundary conformal field theory. And this is argued by a proof of contradiction. And they show that features of holography are incompatible with having a global symmetry in the bulk. Let me, at this point, make a few disclaimers. So this paper is very long and it's very rich. It has algebraic QFT perspectives, it has lattice perspectives. And so I'm going to focus on the minimal part to argue features of their proof. I'm also going to restrict myself to conformal field theories in dimension larger 2 or larger, with bulks of dimension 3 or larger, to avoid some ensemble averaging situations. And in reviewing their proof, I'm going to restrict to invertible zero form symmetries. They make more general arguments for p-form symmetries, and I will come back to these where appropriate. Great. Okay, so in reviewing the proof, I've decided to separate it into 4 pieces. Oh, 1, 2, 3, 4. But before looking at these things in a bit more detail, let me give a bird's eye perspective of how this is going to go. So in the top, I'm picturing as the cylinder ADS in global coordinates, marked a spatial slice at constant time sigma, and then partial sigma is in the asymptotic boundary. It's a spatial slice of the Q of the CFT. And in addition, so the starting assumption is that we have some bulk operator phi, and it's being acted on by a global symmetry. The first step in the proof lies in using asymptotic conformal symmetries and the definition of symmetry as given in their paper to map this bulk problem onto a boundary problem. In the process, the bulk operator phi is going to be replaced by its CFT dual operator O, and the symmetry is going to be expressed purely in terms of a unitary operator of the CFT acting on O. And the situation is like I've drawn over here on the right-hand side. Because we're considering zero-form symmetries at constant time, the symmetry operator U boundary is going to be space-filling, as indicated by the red squiggly line. The next step in the proof is to use splittability. So this is a property they prove for their symmetries. And the goal here is to decompose space into multiple regions, R1, 2, 3, 4, and 5, and then re-express the symmetry operator in terms of a collection of operators which are supported on these subregions. And then the final and key step, which I'm going to review because this is also the meat of our argument, is that now by entanglement wedge reconstruction, one can show that because the entanglement wedges of all of these regions only do not cover all of the bulk, that one can arrange for situations as shown where it is impossible for the symmetry to act on the bulk operator phi. And this then leads to a contradiction with the starting situation. Okay, so now I want to look at these individual steps in more detail and set up discussion to follow that we also make in our paper. So the first step is to set up the bulk problem. And so the bulk theory is a theory of gravity. It has boundary conditions that the metric asymptotes to ADS metric. And so we have diffeomorphisms. And they come in 2 types. There's going to be bulk diffeomorphisms, which taper off to the identity, and they preserve the boundary conditions. These are going to be gauge symmetries of the problem. And then there are also diffeomorphisms which taper off to isometries of the boundary ADS. And these are going to be, global symmetries. It's going to be the SOD, 2 of the CFT. And so to specify the bulk setup, we're going to have an internal global symmetry act on physical local operators. And this requirement of physicality is going to require these operators need to be invariant under bulk diffeomorphisms. And this requires us to gravitationally dress them. So this is what I've drawn over here, where we take the bulk operator and we attach to it a gravitational Wilson line. And roughly speaking, what this does is that if phi now transforms under a gauge symmetry, then this Wilson line replaces a bulk tensor index by a boundary tensor index and makes it invariant again under bulk diffeomorphisms. Internal global symmetries are then defined to be acting faithfully on these gravitationally dressed operators. One requires them to preserve the boundary point x that the line attaches to, so one doesn't overcount and include SOD, 2 symmetries. And then there's a whole list of other properties. The symmetry needs to commute with the stress energy tensor of the CFT, needs to act locally, meaning that if phi transforms to phi prime, then we attach it's both both are attached to the same dressing line. There needs to be representation of the symmetries on the boundary in the CFT via some unitary operators, and these also need to have certain properties. The main point of these definitions is that, together with the fact that I can use conformal symmetry transformations to map a bulk operator phi onto the boundary and essentially replace it with the CFT dual operator O, is that the definitions are such that, and this is a theorem that they prove, that one can fully retreat onto the boundary. So any global symmetry of a holographically asymptotically ADS quantum gravity theory gives you a global symmetry of the CFT. And so, given this setup, there are a few comments I would like to make. So one can address invertible p-form symmetries in this framework by studying the zero-form symmetries that one gets by compactifying these down. And this is how Harlow and Duguri exclude p-form symmetries. It is not completely clear to me how to extend this intricate definition that they give to immediately cover p-form symmetries in their highest degree. Then it's also not clear to me how non-invertible symmetries are going to work. And the notion of retreating onto the boundary avoids the discussion of what the bulk objects are that are generating these symmetries. And so these are some of the aspects that we're going to address later on. The next step of the proof of no global symmetries in ADS is, so now we're on the boundary and we want to restrict to subregions of the boundary. And the motivation here is derived from studying symmetries with Noether currents. So now we're in the CFT and we're given a unitary operator U, which is generated by integrating, which is built by integrating some Noether current over a spatial slice. And the idea here is that if we decompose space into these regions, R1, R2, R3, and we have this tiling, then decomposing the domain of integration similarly, the symmetry operator decomposes into a collection of symmetry operators supported on these regions. And the input that Harlow and Duguri give is to understand how general this is and to push this notion and show that it applies to all symmetries that they exclude in their proof. And so they make this definition here. A global symmetry of a quantum field theory on this spacetime, RT times M, is splittable on M if for every open spatial subregion, R, there exists a unitary operator V such that if we take an operator O and it lies in R and we conjugate it by these smaller symmetry operators, then they act like the original symmetry, and if it lies outside of the support, then it doesn't act. And it is shown that this property holds for all the symmetries that they're interested in. And some comments I would like to make is that now with the rise of non-invertible symmetries, it is expected that these are generically not split. So one would need to modify the steps taken in the proof to apply to these, because they support TFT degrees of freedom. And so if one introduces a boundary, one typically has non-topological edge modes. Then another thing is that these, like the notion of splittability is dependent on M, the spacetime. And it would be nice to give a proof which relies on properties, well, which doesn't rely on properties of the spacetime. And then finally, also these operators that one introduces are slightly unfavorable from the modern perspective, where one claims that symmetries are topological, because introducing these smaller operators, these are necessarily not topological. Because if they were, I could simply contract them away and the complete symmetry operator would be gone. So it would be nice to also give arguments which remain in the realm of topologicalness.
Max, can I ask a quick question?
Go ahead.
If I have an invertible symmetry and I add, appropriate degrees of freedom in the boundaries when I try to define a little patch, how is that not splittable. I mean, I still get to build it by fusing together those things, right? And then summing over the stuff on the.
Yeah, it's not splittable in the sense that you need to be, I think, very careful in that case what you're doing on the boundary of that.
So it's not clear whether it would be splittable or not, but it could be, right? That there's a choice of boundary.
Yeah, I'm okay. Maybe generically it was a bit strong here, but there are cases.
No, just to understand if there was, because maybe you
Thank
have
you.
Thanks.
Yeah. Hi, Max. I have a question with the splittability. I would have expected that in this holographic setup, even for non-invertible symmetries, they're always splittable because I can just take this brain in the bulk and then just fiber it over some region in the CFT and then move it, or like bring the brain from the bulk and move it to the CFT. And then create some sort of non-topological boundary for that thing. Can't I not always do that in a top-down case?
Okay, so maybe one thing I can say towards that is, so for things to okay, what do I say? So okay, sorry, can you repeat exactly maybe?
Well, maybe make it simpler, just in like the brains at infinity and geometric engineering setup. Yeah, so in this setup, and you can repeat it for a holographic. Take a brain at infinity and then over some subregion move it straight into the bulk. So like this is one way you can take like a topological symmetry operator and like a super Yang-Mills and then create a Wilson or Toth line. So in those cases, you'd always have splittable topological operators there. And I would assume you could repeat the same story for the holographic.
Right. I mean, I think the issue there is that, right, if we put in these properties of brains, so one thing that, for example, brains have as a nice feature is that the top charge in a way is always invertible, right? And so when fusing brains together, you have the notion of one single large brain, and this is due to the top charge being essentially invertible. So this is something that might get lost on you in the general case.
Yeah, maybe we can talk about it at the end. Thanks.
Okay.
Max, before you
Yeah.
go on, is there an independent definition of what you mean by global symmetry in quantum gravity, more generally?
So the way that what I'm going to argue in a second is that, right, that if you pull these operators into the bulk, I mean, this is in part where some of the issues here come from, because both Harlow's proof, Harlow and Duguri's proof, and our proof are going to argue that there is no good notion, and so making it well defined is hard. But we're going to introduce something like the symmetry operators that one might try to associate to a global symmetry in the bulk. Okay. Okay. So now I want to review on the key piece in the argument, and that is entanglement wedge reconstruction. And this is also going to be the key argument or key tool that we're going to use in the argument that I'm presenting momentarily. And so to introduce entanglement wedge reconstruction, one should start with the extrapolate dictionary, which is the statement that if I'm given a collection of bulk local operators phi, which I insert at some fixed radius z at different points x1 to xn, then if I take the limit appropriately scaled of z goes to 0 and push these insertions onto the boundary, then I'm computing a CFT correlation function. Okay, and so this extrapolate dictionary is very good for computing bulk correlation functions close to the boundary or extracting leading pieces from it. But if one wants to probe a bit deeper into the bulk, one needs different machinery. And this is where HKLL reconstruction comes in. And so the statement of HKLL reconstruction is that if I'm given a bulk operator phi, then I can express it in terms of some CFT data and a smearing kernel. And the domain of integration here is purely in the CFT boundary. And the reason you might expect that such a expression should exist is because the operator phi needs to satisfy some bulk equations of motion. These equations of motion have boundary conditions. And these boundary conditions can be expressed using the extrapolate dictionary via the CFT data. And then the equations of motion are a PDE problem, and these can be solved using Green's functions. And so one derives, going through these steps in detail, this expression. Okay, in a little bit more detail, so how does this domain of integration look? So if I take the phi operator in the bulk and I consider its future light cone and its past light cone, then these are going to intersect the boundary in these circles. One in the past, one in the future. And the slanted cylinder in between these is the domain of integration. So this reconstruction method relies on properties of the PDE that the Green functions work. And this is not always guaranteed. And so this works in purely ADS, but in spaces which are asymptotically ADS, generally speaking, one cannot globally reconstruct like this, but only do some partial reconstruction that I'm going to discuss momentarily. And so there are two places that one can improve this HKLL reconstruction. One can improve the Green function stuff, or one can improve the CFT data. And doing both of these is going to lead to entanglement wedge reconstruction. So the first thing one can do to improve the situation is to reconstruct purely from from one given spatial slice, as I've drawn down here with the white circle. And one does this by taking the CFT operators O of x and translate them back in time using the CFT Hamiltonian until one can express them purely in terms of data of this one spatial slice. And doing so, one now can do bulk reconstruction from one time slice. The next improvement, which then leads to entanglement wedge reconstruction, or also with, in this case, in the context of ADS known as Rindler reconstruction, is the following. I have this region R on the boundary, and one can construct operators in the entanglement wedge of R purely using CFT data on R. And the statement roughly is that I consider this boundary region R, I consider its domain of dependence. This is some causal diamond on the boundary, and then firing light rays into the past, into the future, into the bulk. Intersecting these is going to cut out the entanglement wedge. And there's a formula similar to the above, where I can reconstruct every phi in the entanglement wedge using operators of the CFT on R. And how this roughly works is that the Green's function in the HKLL discussion is not unique, and so you can change it, and you can use this freedom to kill off the support outside of the region R. Okay. So the consequence of having this subregion duality is used in the proof by Hall and Tuguri by stating that, okay, so I have these smaller operators on these subregions, and they can only implement global symmetries on operators in the entanglement wedge of R, and they do not act on operators in the entanglement wedge of the complement. And this leads to the contradiction that I outlined above. Okay, having reviewed this proof, I want to now give some arguments of what the bulk dual of a topological symmetry operator should be, and how to argue for no global symmetries in the context of non-invertible symmetries. So to set up the problem, we're going to start in the conformal field theory. N is going to be a topological operator. It's going to support some TFT. This TFT is described by some Lagrangian, and I'm denoting its world volume degrees of freedom by A collectively. The symmetry action of N on some charged operator O is written like this. O maps to O superscript N. And then we also have the bulk reconstruct of O, which I'm going to denote by O tilde. And it's given by this smearing kernel expression that I motivated above. And so the setup so far is the one depicted here, where we have O, it's bulk reconstruct O tilde, and on the boundary N. And having drawn this picture, the question now is, what is the bulk dual of N? Does something like N tilde exists, and is N tilde topological? So to source some intuition, let me assume for the moment that N tilde exists. And so the radial direction in the picture above here corresponds to the energy. And so we can do something like holographic RG flow to understand what might happen if we try to pull N tilde into the bulk. So here I've drawn pictures at different values of Z, so fixed radial slices, Z equals 0, larger than 0, and then some critical value. And I've also indicated a grid, which is supposed to track this RG flow. So going from left to right, we can resolve less short distances. And okay. So on the left-hand side, we have the operator O. It's being linked by N. Then going into the bulk and assuming that N tilde exists, these smear out, but at small z, we can still distinguish the two. And then if we keep pushing deeper into the bulk, there's going to be some critical value where everything's in one cell. We can no longer distinguish N tilde and O tilde, and they smear into the bulk reconstruct of the symmetry transformed operator. And the statement, so what entanglement wedge reconstruction applies in this setting, is that Z star is finite. So here I've drawn the pictures from a different perspective. So on the left, we have O and N on the boundary. We can put them inside of some causal diamond and determine the entanglement wedge. And the right-hand side then shows how the bulk reconstruction works. So initially, we reconstruct O, then they smear, and then we get the bulk reconstruct of O tilde superscript N. Okay. With this motivation, I would like to now argue for the claim that this N tilde exists and that it's not topological. And this argument is going to proceed by comparing these two configurations, 1 and 2. So the right-hand side is the control. Here we've just inserted a CFT operator O on the boundary, and we bulk reconstruct it, giving O tilde, and nothing special happens. On the left-hand side, we've inserted O and N in the CFT boundary. And so now we can consider two limits. We can consider N shrink it onto O, link O very tightly, or we can consider the opposite limit where we've made it very large. In the first setting where we've shrunk N onto O, we know that we are bulk reconstructing O tilde N. So in that picture that I would draw there would be purely purple. In the other limit, I can draw a smaller entanglement, smaller causal diamond around O. And I know that at least for some values of radii, I'm bulk reconstructing O tilde. And so the generic configuration, which I'm showing here, is the one where is the intermediate one, where there's similar to what I was trying to motivate before. We know that we first reconstruct O tilde, and then there'll be some transition to O tilde of N. And so this is so far there has been no mention of the N tilde operator. And so first we can argue for its existence by stating that, well, if N tilde didn't exist, right, then we start reconstructing. There's no N tilde, so if we start reconstructing in red, we continue to reconstruct in red. And so the fact that there's this transition region tells us that there must be some other object present in the bulk. And then to argue that n tilde is not topological, we notice that if n and n tilde were both topological, then these two configurations differ only by the insertion of topological quantities. And so in particular, they should have the same stress energy. But in this transition region where this could be as simple as a phase rotation, where we go from O tilde to O tilde superscript n, there are derivatives as the profiles transitions from one to the other. And so there'll be stress energy localized near z equals z star. And so we run into a contradiction unless n tilde is not topological. So to account for this difference in stress energy, n tilde needs to be not topological. And so this is the existence proof. Sorry, this is the existence proof and the fact that n tilde is not topological. Let me also quickly make the same argument for -1 form symmetries. In the above, I implicitly used that I was positive codimension in the boundary CFT. And so for -1 form symmetries, right, we needed the operator O and O tilde to argue for the existence of n tilde. If we, for the moment, pause that and just assume that n tilde exists and want to show that it's not topological, for -1 form symmetries, we can basically run the same argument as I just presented. So here's a CFT with some parameter lambda transformed by n. One then pulls n into the bulk and gets some wall n tilde and a CFT with the untransformed parameter. Then one can look at the bulk field, which corresponds to this parameter. It's going to, again, be transformed as it crosses n tilde, and there'll be some stress energy there. And so to avoid contradiction, n tilde also needs to be not topological. But the key part of the argument is exactly summarized in these two configurations. So let me pause here for the moment and see if there are any questions.
Hi, can you hear me?
Yes.
I wanted to ask, in the proof for the -1 form symmetries,
Yeah.
you said something about the local field.
Yeah.
So what you mean is will be like the dual of the marginal operator in the CFT?
I mean the dual of the parameter that the -1 form symmetry shifts. So there'll be some lambda, and there'll be some bulk field whose boundary value sets that value of the parameter. And I'm talking about that bulk field.
Did you
Okay,
assume
thank you.
that there is an exactly marginal operator for each parameter?
Right. I think so. I think lambdas need to be exactly marginal, yes.
Okay, thank you.
Thanks for the question.
But Max, just following up on this, so
Yeah.
if you assume that there is already a marginal operator for the parameter, it's like saying that there is no -1 form global symmetry in the bulk, no, that is gauged.
Right. I mean, yeah, so it's consistent with that, right?
But then it's not a bit circular, like you're already assuming the answer in a sense, or maybe I'm not
Okay, no,
following.
so this -1 form symmetry part is not supposed to be independent of what you just said. I wanted to demonstrate that. So in the above, right, there are two things that are being shown: existence and non-topologicalness. And the existence part requires to consider both O and N, and the non-topological part just requires you consider N and N tilde. And so in the -1 form symmetry part, we don't have this existence proof because we don't have the O, but the argument also covers exactly what you just said, that it is not topological. Yeah.
Okay, fine, just go on. I need to think.
Okay, thanks. Okay. So, right, so what we're claiming now is that there is some object n tilde, non-topological in the bulk, corresponding to some topological operator in the CFT. And then there's a constraint that, of course, if we bring n tilde back to the boundary, it needs to reduce to n. And we can use this constraint to parameterize our ignorance. And so n tilde in the bulk is going to have to look like this. So let's start off, there's the TFT part, which we can basically read from the CFT. Then there are some non-topological terms, which we cannot say a lot about, but I will address them momentarily. We still have the world volume fields of this object. And then there is this dressing factor Z out front, because there's no guarantee that in pulling off the symmetry operator n into the bulk, that you get a genuine operator. There could be something stretching back to the boundary. And so just to keep track of, well, to allow for this possibility, we have this factor Z out front. Okay, so this is the general form that one expects. And then there are also some estimates one can make about the non-topological pieces. So first of all, one expects that the world volume action of the same codimension n tilde has this form. There's some tension and there's some world volume tensor. For D branes, right, this would be metric pulled back, and there's two form pulled back the world volume field strength. And then there are the topological terms which I described above. It's very hard to say something about this world volume tensor and what the field content is of the branes that we're predicting. But one can give some constraints on the tension.
May I ask a question?
Yeah,
So
go ahead.
I'm sorry, I should have asked earlier. So when you write n of z, so you define it for each z, there is an operator. So in the previous slide, you have this figure where object extend to the bulk. So are we supposed to consider some particular slice of this at z to define operator?
So, right. So in the same way that I have a local operator and that becomes a local operator in the bulk, I'm saying that n is some, if n is an extended operator on the boundary, it's also going to be some extended operator in the bulk. But if I do bulk reconstruction, right, then I'm going to generate this profile, n tilde of z.
Okay. So in the bulk counterpart, is there any connection of this to Gukov-Witten operators when you are considering zero form symmetry, for example?
Yes, there is. And this was an example I was planning to give in a second.
Okay, so you'll explain the connection later. Thank you.
Thanks for the question. Okay. Okay, so I wanted to give you some rough estimate on the tension. And so the tension is, well, on dimensional grounds, it's associated with some length scale. And this length scale is to be interpreted as the Compton wavelength of this object, n tilde. And so we can bound it from above by the ADS radius. And this is because, right, we saw that we predicted n tilde using some bulk reconstruction argument. And this tells you that the smearing takes some time. And so if L star were of the same order of magnitude of LIDS, then as soon as you pull it in, it would smear everywhere close to instantly. And this is not the case. And so there is this bound on L star. And then because we're constructing n tilde in a semi-classical gravitational theory, it's bounded from below by L Planck. Okay. And now to come to Hiroshi's question, I want to consider something. And we're going to consider a U10 form and a non-abelian zero symmetry with some continuous Lie group G. And we want to consider in both cases, the boundary operators will be generated by some Noether current. And we want to characterize the bulk dual. And it's very hard to, as I said before, we can only really say things at the moment about its topological sector. So I'm going to restrict to saying something about its topological sector. Okay, so for the U1 zero form symmetry, right, we have this zero form symmetry, and this zero form symmetry is going to come with a background field A1. The bulk, there's going to be a corresponding bulk field whose asymptotic value sets small a1. And so we claim that pulling n eta into the bulk is going to produce an operator of the same dimensionality. It's codimension 1 in the boundary, codimension 2 in the bulk. And it's given by this Kukov-Witten operator that one gets by integrating the dual of the field strength in the bulk across some manifold yd minus 1, which might sit at some value of z. So here is some picture that I've drawn. And indeed, one can argue that if one takes now the limit of one pushes this Kukov-Witten operator back onto the boundary, then one recovers this topological boundary operator n eta. And the way that this computation works is that one can express this integral up here via an integral over some chain which is bounded by the support, the original support. The integrand is replaced with df2. Then one uses the equations of motion. An intersection in the bulk becomes a linking of the boundary. And this then it reduces exactly to the U1 zero form operator on the boundary. A more interesting example is the non-abelian case, because there, right, we can try exactly the same thing. We're going to characterize a boundary CFT operator via some element in the Lie algebra, and then we're going to write down this invertible operator. And we now want to do the same thing. We pull it into the bulk, but in the argument before that, we get this genuine Kukov-Witten operator, at least in the topological sector. It's very crucial that we had this equation of motion. And so the equation of motion now in the non-abelian case is different. We have a covariant derivative. And the consequence of that is that if we now pull it into the bulk, we will generally expect that there is some object stretching back to the boundary. So we get a non-genuine operator. And this is consistent with everything that we know about Kukov-Witten operators, because here we've labeled the symmetry operators by elements of the Lie algebra. But we also know from very general considerations that Kukov-Witten operators, they are genuine operators, and they are labeled by conjugacy classes. And so, right, we have no expectation that we should be able to pull one of these guys here into the bulk to get a genuine operator.
May I comment on this? So in my paper with Daniel, actually, we did discuss connection to the Kukov-Witten operator. And in that context, we actually suggested we integrate over the conjugacy class of the group. So that way you can define gauge invariant operator on this localized at Z rather than having this. Yes.
That is the way that one would, okay, so the point I'm making here is what you said, Hiroshi, is correct, right? To get a genuine operator, you need this integrating procedure. But, right, what I've argued for above is that any symmetry operator on the boundary should pull off to something. And so I'm trying to supply an answer for what it is in the case where I'm pulling off one of these guys, which is without this averaging procedure.
Oh, okay. Thank you. Yeah, I understand the difference.
Thanks. Okay, so I'm already over time, so let me quickly summarize. So the main point to take away from this talk is that this gives a proof for no global symmetries in asymptotic ADS. So this includes things that in the CFT would be P-form symmetries with P equal or larger than -1, and non-invertible symmetries. And then more generally, what we've argued is that any symmetry operator in the conformal field theory should pull off, or it predicts, some extended object like the brane in the gravitational bulk. Things that I haven't addressed and that we comment on are lower form symmetries. So these are symmetries, like p-form symmetries with p smaller or equal than -2. Right, there's some, this is a valid idea. And then we comment on things that Miguel was saying before about, we have some edge modes in the splittable case, and we can formulate splittability using these and fusing operators back together by integrating out edge modes. And so we comment on these situations too. But let me stop and thank you for your attention.